Okay, let's look at the expression for energy again. So energy was P0 times C, which was mc square over the square root of 1 minus u square by c squared. This is the exact expression for energy in special relativity. And let's plot this energy of a particle as a function of its speed. Okay, so the speed can only be between 0 and 1. At a speed of 0, the energy is just mc square. Okay, and we can write this as gamma u times mc square, where gamma u is 1 over the square root of 1 minus u square by c square. So if you recall the behavior of gamma as a function of u, it starts at 1 and then it rises, okay, to infinity as u goes to the speed of light. So energy versus u would look something like this. At low speeds, what you would see is that there is a correction to the energy, which is half m times u square. Okay, that is, it behaves like a quadratic function of u for small values of u. But as u gets larger and larger, the energy goes on increasing, okay, till you reach infinite energy when you approach the speed of light. Sorry, this is when u approaches c. Okay, or in other words, I can go on, if I think of this as the control variable, that is, I can go on pumping up the energy of a particle, but I will never get it to exceed the speed of light. I can only get it asymptotically close to the speed of light by going on increasing its energy. In fact, it would cost an infinite amount of energy to accelerate a massive particle to the speed of light. Okay, so the speed of light becomes an absolute limit for the speed of any particle, because it really requires an infinite amount of energy to get you there. Okay. Now we could ask something else, which is we could look at massless particles. For example, light particles, particles of light, photons. And for these massless particles, okay, this relationship doesn't quite make sense because the mass goes to 0, but the speed of the particle also goes to c. So the numerator and denominator both go to 0 in that limit. So it's not clear what the limit is. However, if we look at the form of energy momentum that we had derived over here, the relationship between energy and momentum takes this form. The limit of this equation is well defined in the limit that the mass goes to 0. So in this limit, what we would get is that the energy of a particle is equal to, so the exact expression is this, and this goes to, in the limit mass goes to 0. Okay, or energy is P mod P times C for a massless particle. So what we see is even massless particles can carry energy. Okay, they can carry energy by virtue of having a momentum. Okay, in fact, you can, if the particle has 0 energy or 0 momentum, so if it has 0 energy or 0 momentum, such a particle would never really exist. Okay, so to exist, it must always have some small, at least some small finite momentum or finite energy. Okay, so if we look at the exact expressions for energy in terms of velocity, so mc square over the square root of 1 minus u square by c square. We're going to a very peculiar limit where the mass goes to 0 and the speed goes to the speed of light. Okay, and we're saying in that limit, whatever this limit is, there is some energy associated with that. And for momentum, again, we're going to a limit where the mass goes to 0 and the speed goes to 0. And whatever this limit, there's some momentum associated with it. Okay, and the energy of the particle is just related to that momentum times c. Now, what this also tells you is that the only way that a particle of 0 mass can exist is if it's traveling at the speed of light. If it's traveling at any other speed, it would have 0 energy and 0 momentum. Okay, and therefore it would not exist. Okay, so massless particles have to travel at the speed of light. And they carry energy and momentum. Okay, that is, a photon can push things around, okay, by transferring its momentum to something else. Okay, and in fact, you see something amazing here. Okay, it's not that the speed of light is special, it's the speed c which is special. Okay, and photons just happen to travel at the speed c, or this limiting speed of special relativity, because they are massless. And if we were to discover any other massless particles, assuming that the laws of special relativity are right, those particles would also travel at the speed of light, c. Okay, so any massless particles in 2015, we discovered gravitational waves, okay, which are like electromagnetic waves. So they're made up of particles called, hypothetical particles called gravitons. We haven't seen the individual particles, just like before we had discovered individual photons, we knew about electromagnetic waves or light. We've discovered these coherent waves of many photons or many gravitons called gravitational waves. And to the best of our observations, these gravitational waves, which are expected to be carried by massless particles, also travel at the speed of light, c. Okay. So it really does seem like any massless particle, if we were to discover more in the future, would also travel at the speed of light, c. Okay, and the speed is really the thing that is fundamental. It's not light that is fundamental. Okay, and again, just a reminder that this is the speed at which massless particles would travel in a vacuum. Travel at c in a vacuum. Now, let's explore an implication of the equivalence of mass and energy. The fact that mass can be converted to energy means that sometimes we can, in certain subatomic processes, we can get tremendous energy outputs by conversion of mass to energy. So let's look at a particular example. So, of course, you know of particles called electrons, which orbit the nuclei inside atoms. But it was discovered that there are also antiparticles of every particle. So the electron has an antiparticle called a positron, which has exactly the same mass as the electron, but an opposite charge. And now it was also discovered, this was in the first half of the 20th century, that electrons and positrons can annihilate to give you pairs of photons, particles of light. So we could ask now, supposing I take an electron at rest and a positron at rest, so an electron at rest and a positron at rest. So I bring together this matter and antimatter, and I see what the energy of the outgoing photons is. Okay, so I want to know what is the energy of the outgoing photons when an electron and a positron annihilate with each other. So the way we would do this is quite simple. For any process, no matter how many initial particles we have, so let's suppose these are our initial particles and these are our final particles. Now, this is a closed system, right, which is transforming. We're assuming that there's no external energy or force being applied to the system. So what should be true is, from Newton's laws, the sum over 4 momenta of each of these particles, so p mu I, sum over I, d tau, this should be 0 because there's no external force acting on all these particles, which means that the sum over I of momenta, 4 momenta, is conserved. Okay, that is, whatever it is initially is the same as whatever it is finally. So now if we look at this reaction and we write down, so our initial state looks something like this. Our initial state is just an electron and positron at rest, and we're assuming that they're almost or right next to each other so that they can come into contact easily. And so if we write down their initial energies, so p mu, the initial 4 momentum vector, it's E by C, and then we have various momentum components, px, py, pz. This is for each electron separately. And if you'll recall, the energy square was mc square whole square plus p square c square. Now, if the electron and positron are at rest, the velocities are 0, and that means the momenta are 0. So the energy is purely due to rest mass energy, so E is mc square, and px, py, pz are 0. So what this tells us is the energy of the particle by C is mc square for each particle, and if we take both the electron and the positron, the 4-vector sum for both of these will be 2mc square, because both electron and positron have the same rest mass, by C 0, 0, 0. Okay, and now for the final state, we'll assume that you have 2 photons, and these photons have to be produced back to back. Okay, without loss of, it has to be true, otherwise they would not conserve momentum. Okay, so at least in the reference frame where the electron and positron are at rest. So in what is called the center of momentum frame, that is the frame in which the electron and positron have no net momentum, in that reference frame, the 2 photons that are produced must be produced back to back, because if they're produced at some angle relative to each other, then there will be some direction in which the net momentum is non-zero, and therefore momentum would not be conserved. Okay, so the fact that momentum is conserved implies that the photons have to be produced back to back. And whatever that axis along which the photons are produced without loss of generality, let's take that to be, we'll call that the z-axis. Okay, so now for each photon, we can write down the 4-vector. So let's say for this photon and this photon, it's E by C, px, py, and pz. Now recall that for a massless particle, the energy is just going to be P times C, or the magnitude of P times C. And Px and Py are 0, so all of the momentum is along the z direction. Okay, and so we can take Pz to be the magnitude of momentum is the same as the z component of momentum, and therefore E will just be mod P times C, and we can write this now, the 4 vector, as E by C, or we can write mod P as E by C. So 0, 0, E by C. Okay, so these are the 4 components of the 4 momentum of photon 1, and for photon 2 it would have exactly the same magnitude of energy and momentum. It would have the same magnitude of momentum. That's easy to see because the momentum must be back to back to conserve momentum, and therefore it would also have the same magnitude of energy because energy is related to the magnitude of momentum. Okay, but in this case the momentum is along the negative x direction, or negative z direction. So now if we add up these 2 components of photon 4 momentum, what we would get is the z component, net z component is 0, okay, as expected because of momentum conservation. And the total energy is 2E, and the component in the 4 vector is 2E by C. Okay, so now what we can do is we can equate the initial 4 vector that we had for the electron plus positron system to the net new 4 vector that we have for the 2 photon system, and we can solve for the value of E. Okay, so if we do that, what we would find is 2me c square, which is the initial energy of the system, is equal to 2E, where E is the energy of each photon. Okay, so the energy of each photon would just be equal to mec square. Okay, so this is now the energy of the photon. It's not the energy of the positrons or electrons. So what has happened is, in this process of what is called pair annihilation of electrons and positrons, we have converted the rest mass energy of the electron and positron into kinetic energy of the photons. That is, there is no rest mass energy now in the final state. There is just kinetic energy of these photons. And we can ask, how much kinetic energy do they have? Can we calculate this number? So you would find, if you plug in the mass of the electron, that the energy of each photon would be 0.5 mega electron volts. That is 10 to the 6 electron volts. Now, you could ask, well, how much energy is this in common units like joules? And if I convert this to joules, this would be about 0.8 into 10 to the minus 13 joules. Okay, so this seems like a very, very tiny amount of energy. Okay, and the mass of an electron, if you'll recall, is 9 times 10 to the minus 31 kilograms. Okay, the mass of the electron is very tiny, and the energy released when you convert this rest mass into photon energy, or photon kinetic energy, is also very tiny. However, there is an important sense of scale which we should keep in mind. So you could ask now, supposing I had a huge collection of electrons. An electron is, after all, a very tiny subatomic particle. But typically, if we're performing a process like this, let's say in bulk at some scale with a large number of particles, then what we would have is we would be converting a macroscopic amount of matter. So let's say we convert 1 gram of electrons. So many electrons. Okay, and this 1 gram of electrons would have of the order of Avogadro's number of electrons. Okay, it would actually be about 1,000 Avogadro's numbers. So something like 10 to the 26 or 10 to the 27 electrons. We would be converting the mass of these into photons. Okay, so the total energy in all the photons that you would produce in the annihilation of 1 gram of electrons and positrons. So per electron and positron, the total energy released in photons would be 1 gram times c square, m times c square. And this m is 10 to the, so in SI units, this is 10 to the minus 3 kilograms. C is 3 times 10 to the 8 meters per second whole square. So if we square this, we would get 10 to the 17, so 10 to the 14 joules of energy, okay, which is a tremendous amount of energy from just 1 gram of electrons. And this amount of energy release is about the total energy consumed by a city over the course of 1 year. A typical city over the course of 1 year consumes this much energy. Okay, so you can imagine what a tremendous amount of energy release this is if you were able to tap in to the rest mass of particles and convert those into energy. It's quite difficult to actually convert rest mass of particles into energy at scale. This happens in typical chain reactions inside fission reactors, where not the total mass, but a part of the mass is converted into kinetic energy or other forms of energy in nuclear reactions, and also in fusion reactions inside the sun. Rest mass energy is converted into kinetic energy. But again, this requires such high temperatures and pressures, and this has not been done in controlled environments on the Earth.